Okay, let's talk a little bit about Chapter 6, the formulas, right? The equations that we're coming across. So, work is equal to force times distance, right? So, the units would be force is Newton. We learned that in previous chapters, and distance would be in meters, so Newton meters, and we're calling a Newton meter a joule, right? But a Newton is a kilogram meters per second squared. So a joule is equal to a kilogram meters squared per second squared. Because a Newton is a kilogram meter per second squared, right? Force equals to mass times acceleration, meters per second squared. If you multiply by another meter, you get meters squared. That's equal to a joule. We're saying that that is the unit for work. Okay, well, what about energy? So kinetic energy, if you're moving, right? They're calling that kinetic energy. And we learned that kinetic energy is equal to 1/2 your mass times velocity squared, 1/2 mv squared. So let's look at those units, right? So mass would be a kilogram. Velocity is meters per second. But if you square that, it's meters squared per second squared. And look at that. Kinetic energy is the same units as work. Voila! Okay? Yeah, so work and energy, right? Right? We use it slightly different, but it's an equivalent phenomenon. Kilogram meter squared per second squared. Okay. Now let's look at potential energy. Okay, potential energy. So if I have a mass and I hold it up in the air, right? So if I have this marker and I pick it up, it now has potential energy. Because if I release it, the energy is going to go down and smack into the tabletop, right? So potential energy is mgh, mass times the acceleration due to gravity times the height, right? Potential energy is equal to mgh. Let's look at those units. So you're going to have mass, so it's kilogram. Then the acceleration due to gravity is meters per second squared. And then h, it's a height, which is going to be in meters. So this kilogram meters times meters, well, that is kilogram meters times meters is meters squared per second squared. And it's the same, potential energy has the same units as kinetic energy. Well, of course it does. Potential energy, it's the potential energy, but you know, if you have a pendulum, right? Here, if I hold the pendulum way over here, so it's all potential energy. If I release it, now it's converting to kinetic energy. And now when it's up at the top again, just for a moment it stops. It's all potential energy, right? Right at the bottom, there's no more potential energy. It's all kinetic energy, right? So it makes sense it's going to have the same units, right? Let me put around here too. Look at this. Ta-ta. Wait, let me. Science. This is why you study science, right? This is why everyone needs to study science. Let's keep going. We're on a roll. We're on a roll. So let's talk about a spring. So potential energy, if we're talking about a spring. So potential energy, right? So before it was like, so if I'm holding it up in the air and let it go, that's mgh. But if I had it on a spring and pulled it back, well, that's also potential energy, right? And we learned that that is 1/2 K, right? The spring constant, x squared, okay? The units for that. Well, the units for a spring are Newton meters, right? The spring constant are Newton meters. And then x squared, which is going to be meters squared, okay? So now we have, so this meter here will cancel with the square, and you end up with Newton meters, and a Newton meter is equal to a joule. We determined that way in the beginning. And you're back where you did it again. So it's the same. A Newton meter is equal to a joule. Okay. So work, kinetic energy, potential energy, whether it's due to gravity or a spring, right? Joule. Okay? And yeah, you notice I like breaking it down to make sure my answers are right. I like converting it into a kilogram meter squared per second squared, but a Newton meter is defined as a joule. Okay, let's go with power. So power. Now this is something a little bit different now, right? So power. Now a watt we're used to, right? So a power is equal to work over time. I'm going to use a script T so we don't get it mixed up with my pluses, right? So that is equal, so work divided by time, and we call that a watt. We call that a watt. So don't get, okay, I got to make this watt different than this. I'm going to make this watt. This watt is, that's work. This is a watt. So I'm just going to write it out. It's the guy's name, Watt. Right? He was a genius that worked with all this stuff way back when. So it's a watt. So work over time is a watt. We're used to a watt, right? If you have a 100-watt light bulb, right? We're the old-fashioned kind, not the ones not the energy efficient ones we have now, but the old-fashioned kind that gets warm, very warm, right? 100 watt. Well, if you had 10 100-watt light bulbs, that would be a kilowatt, right? Now, here in the United States, we don't use joules. We use kilowatt hour. You may have heard the term kilowatt hour. So instead of saying, so for us, when we want to talk about energy, we use kilowatt hours, which if you multiply work divided by time, right? Now you have watt time. I'm just pointing that out. It's not on the exam or anything, but I'm just pointing out the difference between our common usage of how watts are and how it relates, right? But a watt is energy time. It's the rate that you're using energy. Okay? There you go.